Hello everyone. In this session we will discuss the next topic is the starting torque. So general the torque formula, you know that the torque equal Ks e to naught square into R2 by R2 square plus S x2 naught whole square. This is the torque equation. But we have to find out the starting torque. It's at starting the slip of the induction motor is 1. Why it is 1? The speed will be 0. The speed will be 0. Then slip become the 1. Just substitute in that, you will get torque equal here K into slip value is 1 and E2 naught square into R2 by R2 square plus x2 naught square. Okay, the final is the starting torque TST. The starting torque equal K into E2 naught square into R2 by R2 square plus x2 naught square. X2 naught square. Okay, here we are using the same condition, that is if all drops are neglected. If all drops are neglected, then the supply voltage will be equal to the E2 naught. Then we can tell starting torque directly is proportional to the V square. So we can give the starting torque is proportional to the V square. Why? It is in the formula itself, it is the E2 naught square. It is E2 naught square. Yes. So this here the V is phase voltage. Don't confuse here. V is the phase voltage. Right. And this is the first observation. And if you go for the second observation, in the second observation itself, generally the rotor resistance R2 value is approximately 0.1 to 0.2 ohms. And rotor reactance X2 will be equal to the 1.5 to 2 ohms. 1.5 to 2 ohms. So if you observe the both the things, the R2 will be very less compared with the X2 naught. So we can neglect the X2 naught. We can neglect the R2. So directly we can write the starting torque is proportional to the rotor resistance. Neglect X2 naught. Just look at here. Here the combination is there, R2 square plus X2 square combination is there, but we can neglect here. And if you add the external resistance to the rotor, then the starting torque will be improved. So by adding the external resistance, any resistance, we can improve the starting torque. So generally, in case of slip ring induction motor, the external resistance already available. By adding additional resistances in rotor, starting torque will be improved. The starting torque will be improved. So the starting torque will be affected by this, but not maximum torque. Keep in your mind, by adding that, but not maximum torque. Only external resistance will increase the starting torque, but not the maximum torque. Go for the next observation. The third observation we can write like this. Here the starting torque, just observe here, the starting torque compare with that, but if you take individually, inversely proportional to the x2 naught square. Starting torque is inversely proportional to the x2 naught square. x2 naught square. What is x2 naught here? x2 naught, the rotor leakage reactance. Okay. Here we can tell that the starting torque is inversely proportional to the square of the leakage reactance. The starting torque of squirrel cage induction motor little compared to the slip ring induction motor without additional resistance. For example, we don't have additional resistance. Just look at here. Okay, we can give one statement: the starting torque of squirrel cage induction motor is little more compare with the slip ring induction motor, because the leakage reactance is less in case of this. That's why starting torque is little more without additional resistance. For example, we have the slip ring induction motor, it doesn't have additional resistances. That point is important. Without additional resistances in the rotor circuit. Resistance in the rotor circuit. Yeah. So if you are not considering the rotor resistance, then the starting torque of the squirrel cage induction motor is high. But we have the rotor resistances. That's why overall that will be high. And fourth point. Here the fourth point is starting torque depends on type of slots. Depends on the type of slots. How it depends? So same thing as the maximum torque. x2 naught is open slots is less compared with the x2 naught semi open slots. Less compared with the x2 naught closed slots. And in this we can write the starting torque of open slots is I, and the starting torque of semi open slots better, and starting torque of closed slots are somewhat better. Closed slots are somewhat better. Next, here the next point is fifth point. Starting torque is depends on the and air gap length. That is also important. Starting torque depends on air gap length, which has more air gap, which has the less air gap that has more starting torque. Inversely proportional. Less air gap has more starting torque. So compare with the squirrel cage and slip ring induction motor. The starting torque of the squirrel cage induction motor. So the starting torque of the squirrel cage induction motor little more compare with the starting torque of the slip ring induction motor. The starting torque is high compared with that. This is also important thing. Okay. So here some electrical factors are also affecting the starting torque. So we can give about the electrical factors affecting on the starting torque. So up to now these are the mechanical factors affecting on the starting torque. Almost maximum torque, starting torque has the same relations. The final equation, approximate starting torque final equation is like this. The final equation, we can eliminate the resistance. The starting torque value is depends on the K E2 naught square R2 by X2 naught square. X2 naught square. So this is about the starting torque. This is about the starting torque. Okay. Yes. So for this, how it depends on the electrical factors. So once again we will write the starting torque formula, that is Ks E2 naught square into R2 by X2 naught square. Okay. Here just starting torque is, just observe here, this is the V, this is the frequency, and we have another frequency. So it will depends on two things. One is voltage per frequency into, again we have the 1 by frequency. Depends on the two things. If you take the case 1, in the case 1 voltage will be variable and frequency will be variable, then voltage per frequency is constant. Voltage per frequency is constant, that gives the flux also be constant. That time starting torque, this part will be constant, will be depends on only the frequency. If we go for the case 2, in the case 2 itself, both are variable. Case 2, suppose voltage is constant and the frequency is variable, then V by F not equal to constant and flux is also not equal to constant. Then but starting torque is proportional to the 1 by F cube. If you go for the case 3, in the case 3, for example, V is variable, frequency is constant, then directly V by F is not equal to constant and flux is not equal to constant. Then the starting torque will be proportional to voltage square. These are the three conditions. So this is about the starting torque and starting torque parameters. Okay, this is the starting torque approximate equation. These are the parameters affecting on the starting torque. I hope all of you understand the session. Thank you.